Good morning, everyone. Thanks to the organisers for giving me the opportunity to speak here. My name is Tom Killestein. I'm a postdoc at the University of Turku in Finland. And today I'm going to give you a brief overview of the Gravitational-wave Optical Transient Observer, a multi-hemisphere, multi-site sky survey that is currently underway. So GOTO was really born out of the demands of multi-messenger follow-up. So the standard 170817 slide for any multi-messenger people in the audience, this profound event that has really changed the way we look at things, powered by triggers from the gravitational wave detectors. But we should be cautious that not all localizations are as beautiful as this one. Many are horrific and span significant fractions of the sky. And this really demands a different type of survey capability to what we have at the moment, something that is dynamic and can trigger itself to follow these events wherever they may go off in the sky. Alongside this, a background of the transient zoo unveiling itself over the past few years and really pushing to shorter timescales. This blob up here is a cow. It doesn't really come out well on screen, but extremely luminous events like 2018 cow have unveiled themselves, as well as some perhaps more interesting things going on in this gap region. Until very recently, this was largely serendipitous discoveries, but with advancing survey cadences, we're beginning to routinely access this region of parameter space. This blue line here is the nominal Rubin cadence we've heard a lot about. So there's a lot going on over here that we, again, will only see serendipitously with this large survey. And inside this region, there are many interesting things, ultra-stripped supernovae, kilonovae, F-bots, all the things that we like to put in our paper titles, but also exciting physics. So to get to the main point of the talk, the Gravitational-wave Optical Transient Observer is an STFC key project that has been specifically designed for rapid response GWEM searches. Although these same capabilities lend themselves very nicely to infant transient discovery and fast transient discovery. This is multiple mounts with 8 40-centimeter astrographs. One of these is one of our telescopes. We have 4 of them at the moment. I'll talk about that on the next slide. Each one of these will get down to 20.5 in 3 by 60 seconds over a 44 square degree field of view per mount. So this is a fairly wide and deep survey, although not as wide, not as deep as LSST. We have a rapid response pilot that listens for GCNs and other alerts, and then will tile the sky autonomously. We've been routinely getting onto target within around 2 minutes of the alert coming in, so this is rather fast. And we typically cover around 10,000 square degrees per night. And it's useful to think about this set of axes when talking about transient surveys to place things into context, so cadence, area, and flux. And GOTO very firmly goes for area and a little bit of flux. Of course, LSST is going way into the flux zone. The biggest update for this is that the full GOTO is now here and has been operating for around 9 months now at design capability. So we have 32 telescopes, 32 unit telescopes, 4 telescopes, 2 in Siding Spring and 2 in La Palma, which is giving us a 160 square degree field of view. If they could observe simultaneously, there is a near 24-hour operation. And we have essentially across the middle of the sky this overlapping declination band where both sites can see the same bits of sky, so we can hit up to 12-hour cadence on this. The survey now covers 70% of the visible sky, which is really great. You can see our progress here. There's still a few persistent patches that are hidden by the sun. And we're now regularly reporting supernova candidates to TNS, 17 in the past week. This is all powered and orchestrated by a real-time discovery and dataflow. For the flowchart fans, this is our flow. This figure provided by Martin Dyer. We go from GW to GRB alert to observing in about 2 minutes, from data taking to difference image candidates in about 10 minutes, and 15 minutes latency from shutter close to appearing in our web tooling to seeing the data. So this is an ESO-LSST conference, so I wanted to touch on a few things that are particularly exciting for us, and we hope will be useful in the era of LSST. These modern surveys are really powerful test beds for novel machine learning techniques for Rubin. In particular, there are some unique challenges of these multi-hemisphere, multi-node surveys, which you don't get with a single monolithic telescope. So GOTO, Atlas, Pan-STARRS, other surveys are more modular, and so have multiple facilities with different telescopes. This means they also may have slightly different characteristics in terms of PSF, background, sensor characteristics. And so there's significant in-house development of machine learning and deep learning tooling with, we hope, a big community impact. So I will talk a bit more about our novel real bogus classification scheme on the next slide. We're working on our own in-house contextual classifier, which we've jokingly named Moriarty to go along with Sherlock. And we're also working on light curve classifiers and some semi-supervised QA. You can look at the references here if you want more detail on that. So GoToRB is the project that I led, and essentially we were really concerned here with how can we generate large training sets with minimal human intervention. So we've already heard throughout this week that we're very likely to be swamped by Rubin, and a limiting factor is certainly going to be human eyeballs. So there are 3 steps to this project that are really useful for transient science. So we have a fully automated training set. Solar system people can cheer because we make use of the minor planets here. These are our real detections that we use to train the classifier. And then we use the fact that this difference imaging process leads to high amounts of class imbalances due to artifacts, and use randomly sampled difference image detections as our bogus set. We're interested in finding supernovae in GOTO rather than minor planets, although we also like finding them for our training set. So we come up with this transient augmentation scheme where we combine our minor planets with nearby galaxies to create plausible looking supernovae. And this turns out to have quite a significant impact on the classifier. There's no time to talk here, but we can get essentially a 5% accuracy improvement on supernovae. And we have also been playing around with these Bayesian neural networks to try and quantify uncertainty in our classifications. This is something that machine learning is notoriously bad for, but this really is a crucial ingredient for doing things like active learning. So this slide, big data, big problems. There's quite a few things that are perhaps not significant now, but when we move to these larger streams will become so. I put this mainly here as food for thought, and I'm happy to chat afterwards if anyone has any thoughts. So moving from simulated data to reality, we have to be really careful about things like domain shift, outliers, and artifacts. How to bootstrap the training sets for the classifiers we want, particularly in these very early stages. Monitoring the performance of, correcting issues with, and monitoring for data drift of complex multi-class models in production. This is something that has been a particular challenge with current algorithms. And then bias. We've heard the word bias quite a bit throughout this week. Bias is not an intrinsically bad thing. It's how our models learn. We have to make some inductive bias to begin learning. But the problem is, how do we quantify this and align it with our expectations? I wanted to flag some early science not early science, some recent science that we've been doing and really underscore the importance and reward of TOO observations. Agile scheduling is enabling powerful responsive mode science, and GOTO is really making a significant impact in poorly localized GRBs. So just 3 things here. AT2023 LCR, GOTO managed to constrain the explosion epoch within 1.5 hours. Groups later got a JWST spectrum of this one. GOTO's first afterglow discovery. And then this week, while I've been at this conference, GOTO has discovered the optical counterpart to a high redshift, low luminosity maxi GRB, which is pretty exciting. This slide, I wanted to speak for higher cadence. Rubin cadence is unlikely to be fast enough to routinely find and sample the rises and falls of rapidly evolving transients. And related, how do we routinely find supernovae in their infancy with Rubin with a slightly longer cadence? This is something where I think that existing transient surveys have a real power to be able to provide that coverage at shorter timescales that may be missing from the larger survey. Of course, once you find these things, you can follow them all the way down to 23rd with Rubin. And we really need our bright nearby targets still to generate the large panchromatic data sets we need to make breakthroughs and place more distant universe in context. Something we've been working on in GOTO is this GOTO FAST survey, which is a dedicated high-cadence transient survey, specifically tailored for fast transients and paired with real-time spectroscopic follow-up, which means you get nice light curves, very nicely sampled. Quite a lot of what you find will be CVs, which may be great or terrible depending on your science goals. And to underscore here, even with Rubin, these higher cadence surveys have a crucial role to play. And to wrap up this talk, I wanted to switch direction and talk about a project that's been a real fantastic thing these past few months. And this is Kilonovae Seekers, and this is our real-time citizen science project for GOTO. So we are doing real-time streaming of our candidates to the Zooniverse, where an army of over 2,000 volunteers are looking through them and finding interesting supernovae, and then feeding back to GOTO so we can report these to the community. This started in summer of last year and has very quickly grown to a scale that we couldn't really anticipate. So 2,000 volunteers from 105 different countries, and we've made 21 discoveries so far. It's a particular good thing that we're getting engagement from the Global South, and they are really relishing the opportunity to do this science. And this is going to continue to grow, we hope. So that's a quick overview of GOTO. Happy to take any questions and happy to chat more in the coffee breaks. Thank you.
Thank you very much. And thank you to all the speakers for